Good evening, everyone. My name is Jamil Siddiqui, and I'm here on behalf of Fiveable to present some calculus this evening. I hope everyone's doing all right. If you guys could just start off by just putting something in the chat to make sure I know I'm live and that people can hear me, I'd really appreciate it. Tonight, we're going to be looking at taking derivatives. So let's get started. Our topic tonight is helping students master taking derivatives. This is the first stream that we've done on Fiveable in calculus geared towards teachers and helping you guys get ready to help your students get better at calculus. So if you're a teacher, welcome. I'm happy to have you here. If you're a student, well, you can stick around, but this is really going to be more along the lines of how do we explain the derivative taking process. So I can see Matt is here this evening. Thanks, Matt, for giving me that. I'm glad to know that our sound is working this evening. So here we go. Remember, you can follow us at Think Fiveable on Twitter, Instagram, YouTube. You can get all of our updates and see our schedule so you'll know exactly what topics are coming your way. Tonight in this stream, we're going to be looking at the basic derivatives that your students will need to know on the AP exam. How to pick the correct rule when confronted with multiple rules at the same time, product rule, quotient rule, chain rule. And then how to organize the work to avoid careless mistakes. Because as all of us who've been teaching for a while know, the number one enemy to most of our students is just their carelessness. So can we organize their work so that people can follow it, people can see it, and they can get their full credit that they deserve? So the first thing I want to talk about is what I call the one-step derivatives. Okay, in my world, in my classes, we refer to the derivatives that students are just supposed to know on site as one-step derivatives. In other words, you can just look at it and you can tell me the answer. No work needs to be done. You're just familiar with it. So the one-step derivatives in the world of calculus are, first of all, the derivative of x to the n. The 6 trigonometric derivatives. Your students need to know these backwards and forwards, I always tell them. Along with that, you need to know the 3 derivatives that deal with logarithms and exponential functions. And then the 3 that cause my students the most problems, the 3 inverse trigonometric functions that they need to know in order to perform on the AP exam. Now, when I teach this derivative taking, I usually just start with the first 7. I like to get my students ready and used to the idea of taking derivatives by looking at x to the n and then the 6 trigonometric functions. I feel that if I can teach them the one-steps, the products, the quotients, and the chains using these 7, then incorporating the other 6 is not a big deal because all math works the same. So once you're comfortable taking a derivative and learning how the process works, you're really not all that concerned about what the actual function might be. So these are the 13 derivatives that in my class I say students need to know. Obviously, if you want to increase this list to be more, any derivative that you've done, it's not going to be different the next time you do it. So you could turn that into what I call a one-step derivative. But I prefer just sticking with these 13. The less my students have to memorize, the better off we are. And what you'll see is this is actually a 2-part series. I'm going to be doing a follow-up series on implicit derivatives and inverse derivatives. And you're going to find out that basically the first 7 my students know really well. The last 6, they can actually derive by using some of those other techniques we'll be seeing in our follow-up sessions. So what I want to do is just go over the product, the quotient, the chain rule with everyone really quickly. I know those of you who've been teaching, you're very familiar with it. But what I want to talk about is how I get my students to organize their work. Feel free throughout the evening. If you have any questions or any comments, put it over there in the chat. I'll respond to them as I see them. I want this to be as interactive as possible. So anything that comes across, any questions you have, please let me know. I want to make sure that you guys are getting what you want out of this session tonight. So again, in my class, we usually start off with the one-steps, and we do that for a day or two, and I really, really drill those home. I want my students to be able to recognize them and be very familiar with them. You're going to see some examples of all these rules in a few moments, but I thought it'd be better just to get the rules out of the way and then look at the examples after. So after a day or two of practicing the one-step derivatives and all the different forms that they can come in, my students will come in, I'll be like, all right, I'll put a problem on the board. Usually it'll be something like x squared sine x. And after doing the one-steps, they know how to do the individual pieces, but they've never seen them as factors before. So their first thought is to take the derivative of each factor individually. We talk about why that's not going to work, and then we come up with the product rule. So the product rule that every textbook has that we all know is written in the form that you see on the screen now. I can remember being in high school and being good at math, but not being good at reading math. And that's a big jump for high school students to take, is giving them a textbook and just saying, look at this math and read it and see if you understand it. Notation is usually something that they struggle with. So when they open up the book and they see something like this, my good students, they don't have a problem. But I have a lot of students that just see this and they're reminded of the old Charlie Brown cartoons when the teacher's talking. It's just kind of like, wah, 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 wah. I mean, they see the symbols, but they don't know how to interpret it. I got a question that came up. I want to answer it as they come along. Logs with bases other than e and inverse or inverse trig functions. They rarely ask anything that is not natural log when you're talking about logarithms. With the exponential functions, a to the x and e to the x are both one steps that my students need to know. And I'll do a lot more information about this particular question in the part 2 session that I'm going to be doing. That will be coming up early next week. Okay. Going back to the product rule, what I found was if I could get my students to organize their work, they did a much better job of keeping the product rule correct. Again, looking at this notation, there's just a lot going on. But if we break it down, I ask my students, how many different parts do you see in the product rule? And what they always tell me is that they get that there are basically 4 parts. And what I do is I like to put a set of boxes to illustrate those 4 parts. So what are the 4 parts we're talking about? Well, the first part is f of x. And that always goes in this box right here. I'm very consistent. We do it the same way every single time, so there's never any confusion. So when we're looking at a product rule, we want to put f of x in that box. And then the next part is g of x. Now, students don't need to do any work at all to recognize these. These are the factors from the original problem. And what I always stress to my students is, if you're doing the product rule, this box here times this box here has to go back and be the original problem. I mean, that's what the notation is saying, f of x times g of x. That seems like a really small thing to mention, but you're going to see as we look at some of these problems later on, it's important that we stress it early on. So again, this box times this box always gives us the original problem. So now the other 2 pieces the students need to find, the next one is f prime of x. But by setting up as boxes, what I'm doing for my students is I'm saying, look, forget about g when you're over here. Just focus on taking this one small piece, finding that derivative of f of x by itself, and don't complicate the matters by trying to remember g or g prime or anything like that. And as we continue, the last piece that we're looking for is this guy right here, g prime of x. And he's going to go down that box right there. So again, I would imagine a lot of us learned the product rule, something along the lines of the derivative of the first times the second plus the derivative of the second times the first. I know my calculus teacher, Mr. Daigle, taught me that decades ago, and that's how I used to do it. But there was one day I was working with one of my students, and no matter how hard we tried, they just couldn't keep the parts straight. That didn't resonate with them. So trying to appeal to some other sense that they could understand, we went with a graphical way of doing it and making these boxes. And again, the advantage for my students, you're never thinking about the entire problem at once. When you're in this box, you're just taking one derivative. What is f prime? And when you're in this box, you don't have to worry about f anymore. You're just taking that derivative and finding g prime. At this point, you've got the 4 parts. The only question now is, how do you assemble them? Well, I call it crisscross. And the way it works is we start in that bottom left-hand corner every single time. Again, the idea is to be as consistent as possible so that students will always do things the same ways. I don't like any shortcuts. I don't like any quick rules, because what that happens when I use those, my students are always wondering, is it appropriate to use in this situation or is it not appropriate to use? I like rules that work the same way every single time. So we're going to always start in that bottom left-hand corner, and we're going to get f prime of x times g of x, which if you look at the product rule, that's exactly the first piece of the puzzle that we need. That's my Chris. Now when I go plus, and that reminds students to put the plus in between, and then we're going to come back the other way, and we're going to cross. And that's going to be f of x times g prime. So by using these boxes, the idea is to keep students' work very, very focused on only one problem at a time, and then using the graphic organizer to combine them at the end to get your final answer. So that's how I teach the product rule. We'll be looking at this in examples this evening. So when I say Chris plus cross, you know where I'm coming from on this. Of course, the next rule we want to talk about is the quotient rule. And when talking about the quotient rule, again, a lot of notation going on in this one. But if you really dig into it, what you're going to find is you're going to find those same four pieces. You're going to find f of x, just like we did before. It's going to go in the same place in that box. You're going to find that you need to know g of x, just like before. You're going to find that f prime is hidden in there, so we got to put that in the same place. And you're going to find we've got a g prime right here. So we've got to take that and put that in the same place. So regardless of whether you're doing the product rule or the quotient rule, your boxes are identical in setup. Again, the idea, take a big problem, break it into smaller problems so our students can focus on one problem at a time. Now the question is, how do we assemble the quotient rule? Well, it works the exact same way. When we go and we look, we get the Chris and we get f prime times g, which is the first term in that numerator in the answer. Now, when the product rule, we did the plus going across, there's something mathematically balanced about this time it being minus. Because when we think about division, we think about subtraction being linked. Same thing with multiplication and addition. So the quotient rule is going to be the Chris minus the cross. But the one downside I have with this is students tend to forget the denominator because they're so used to seeing the product rule. So I make a big deal about saying over the original denominator squared. Matter of fact, that is the first thing that they need to write when assembling the quotient rule. If they can remember over the original denominator squared, the Chris minus the cross comes back and it works exactly the way we want it to. So as we go through some problems today, I hope to show you why breaking the big problem into these smaller problems is really useful for my students. Of course, the last rule is the chain rule. And in order to really grasp the chain rule, I actually start setting it up in my algebra classes. I'm going to switch over to my tablet, if you'll just give me a moment, because I want to show you how knowing what's coming in calculus when you're teaching algebra is really, really extremely useful. So if I can just switch over to my other tablet. Okay, so now back in algebra 2, back in pre-calculus, our students are starting and they're starting to use functions. And when we write f of x equals x squared, okay, if you put that on the board the first day of class, or f of x equals x squared plus 3x plus 1, let's say, students in pre-calculus, they're going to be comfortable with this. Students in calculus, they're going to be comfortable with this. But back in algebra, when you're first teaching function notation, this is where I take advantage of setting them up for the chain rule. I'll ask my students, what is the function that you see here? Okay, and when they look at it, they just read it to me. That's what they want to do. They want to say f of x equals x squared plus 3x plus 1. And 99% of the time, I would agree with that. But on the day I'm teaching functions for the first time, I don't. Because I want my students to really dig deep and understand what a function is. To me, a function is nothing more than a rule that we follow to get an output. You take an input, you use this rule on it, you get an output. So when we ask, what's the function here? What I'm asking is, what are you going to do to your input? Well, if you're fluent in math and you speak the language of mathematics well, x squared plus 3x plus 1 does answer that. But again, I think my students need to really build their fluency up in mathematics. So when I say, if I plug in a number here, what am I going to do with it? The first thing we do is we square it. Okay, so that's the first part of the rule, just square the input. Next part is to take that input, multiply it by 3. The next part is to take those two terms, add them together, and then put a 1 at the end of it and add it together. And that's how you'd explain that in words. That gets a little cumbersome if we're in class having to say, take the input and square it, take the input, multiply it by 3, take 1 and find the sum of all those things. So we develop a shortcut notation to use that. And the notation we use, I call them, f of something. And my somethings are blank parentheses. So my students back in Algebra 1, Algebra 2, pre-calculus, they will say to me that the function here is something squared plus 3 times something plus 1. And when I ask them to do a problem like f of, let's say 5, okay, they kind of roll their eyes at me a little bit because I literally make them write something squared plus 3 times something plus 1, and then as the next step, go back and fill in the 5, and then do all the arithmetic that comes with it. And a lot of them obviously are bright enough that they could do this just all in one swoop. But I really, really want them to stress the idea of using these somethings. And the reason for that is because I'm setting them up for composite functions. There's going to be an inside function, and there's going to be an outside function. And the sooner they are comfortable with the idea of just calling this function something squared plus 3 times something plus 1, the easier time we're going to have when it comes to doing the chain rule in calculus. So again, some students I teach them in Algebra 1, Algebra 2, I started there. I'm very fortunate. I actually teach the majority of my kids pre-calculus and have them begin in calculus. So this is something I drive home with them during their pre-calculus class. And now when they get to calculus, they start to understand, because we're going to go back and look at the chain rule now. We're going to see where this really takes on a lot of importance. When we're discussing the chain rule, again, you look at the notation, there's a lot going on there, okay? And students, again, at first have a hard time deciphering this. But I give them these steps, and those steps are, first thing you want to do is you want to take the derivative of the outside function. Step 2, copy the inside. And step 3, most students remember for the most part, because if we're taking the derivative of an outside function at the first step, at some point we got to take the derivative of the inside function. You just have to make sure you remind that that's always going to be multiplied by the derivative of the inside function. Okay, these are my 3 steps for the chain rule. And if I can get my kids remembering these 3 steps along with how to use some things, the chain rule is relatively straightforward for them. So I want to go through and kind of share the basics of how I talk about these rules. Now what I want to do is share the types of examples I give to my students the first week or 2 that they're taking derivatives, so they can start to learn the nuances and the pitfalls and what to be careful of when they're actually taking these derivatives. So we're going to just go back to the tablet, if you'll give me a moment. And again, if you have any questions, feel free to put it out. If you have a comment, something you want to discuss, let me know. We're going to go back to my tablet. And the first thing we're going to talk about is learning your one-step derivatives. Because if you don't know those one steps, the system I've developed for taking derivatives is going to fall flat on its face right away. It's all predicated on the idea of learning one steps. There are several introductory lessons that you can do to get students to develop the derivative of x to the n. If anybody's interested in one, just message me. I'll be happy to share it with you. Matter of fact, you can contact me. I'll put this on here right now. You can contact me at JamilSid312 on Twitter. Message me that you want some of my lessons on developing the x to the n derivative, and I will love to share those with you. Not the focus of what I'm doing tonight, but it's important that your students have a feel for how to take that derivative x to the n. Once they've got that one down, next come the 6 trig functions. And they're all really similar, and students, it's very easy for them to confuse with the trig functions once you start using them. So I'm going to tell you the way I get my students to remember these 6 trig functions. And it's going to sound a little wacky, but year after year, it works really, really well. So we start with sine. And in my class, all my students know that the trigonometric parents love their children sine and cosine very much. And if sine gets something, cosine has to get it too. So when we play kind of just the first thing my students think when they hear sine, because of that, they automatically just think of cosine, which is great because that gives them a way to remember this derivative without a lot of effort. The derivative of sine is cosine. So now we start looking at the next 5. And I tell them that if you can stick with me on the next 2, you'll get the last 3 for free. So I'm going to show you the method that I use to get my students to remember these 6 trig functions, derivatives. If you like it, use it. If you don't, find another way. Because again, everything I show you the rest of the evening is not going to work well if students cannot recognize their one-step derivatives and know what the results of them are. What is cosine? And I just kind of ask my students, okay, what do you think the derivative of cosine is? And you can imagine probably the same thing happens in your classrooms. Get a lot of answers of sine right away. And we know that that's a pretty good guess, but that's all it is. It's a guess. So how do I get my students to remember the right answer? Well, I tell them a little story. I tell them a story about growing up and my mom and myself in my high school career. And my mom made a deal with me early on. She said, as long as you don't get any C's and you get A's and B's, we're going to be fine. You're never going to have to worry about me being angry or upset with your academics. You just make sure that you get A's and B's and no C's. Well, from that time, ever since the time I started getting grades in school, I've always associated C with kind of this negative connotation. And I never wanted to see a C because I knew that would be something negative that my mom wouldn't be happy with. Well, because of that, I can now say this to my students. Every time I see a C, I think about negative. And as we fill out this table of derivatives, It just so happens every trig function that starts with C does have a negative derivative. Okay, so right away, there's one kind of memory game I play to get my students to help them remember, hey, the C's are going to be negative. At that point in time, they're predisposed to the idea that derivative cosine should have sine in it anyway. So my students really don't have that difficult of a time remembering the derivative of cosine is negative sine. And we've got 2 of the 6 done, and we know we're looking for a couple of negatives later on. So now the question becomes, how can we get students to remember the derivative of tangent? Because remember, I said if you get through the third one, the last 3 are going to come from it. So how can we get our students to remember the third one? Well, I want to show you this graphic on the third one. I can remember being, back in 7th grade, getting worksheets in my history class, and they always had a fill-in-the-blank portion to it. And to make matters even easier, there was a word bank to use along with it. So what I've done here is I've set up a template where we've got 3 blanks to fill in, and we've got a word bank. So the next derivative, you may remember, the next derivative I wanted to find was tangent. So if I go down to the word bank and I put tangent up here, well, there's 2 blanks left. There's 2 words left. So I just go through and I fill in the blanks, and secant's got to go there, and secant's got to go here. And all of a sudden, we've now come across the idea that the derivative of tangent is secant times secant, which I'm going to write as secant squared. So that's kind of the one the students have to remember. And I drill this home that day. We're creating a ratio, 2 secants to 1 tangent. I say that over and over again during the class, 2 secants to 1 tangent. Because now that I've got this one, the derivative of tangent is secant squared. If my students can remember 2 secants to 1 tangent, they have a really good shot of remembering this derivative. What about secant now, you ask? Well, let's go back to that little fill-in-the-blank game, and let's play it again, but let's reset the words. The exact same bank, the exact same fill-in-the-blanks, the exact same word bank, but this time the difference is I'm finding the derivative of secant. So if secant goes there, well, I've got 2 left. That means secant has to go there, and tangent has to go there. So now we know the derivative of secant is going to be secant tangent. And of course, that's commutative property. You can write tangent secant if you want. I'm going to be consistent every time I say it. I always say that the derivative of secant is secant x times tangent x. Now, one little thing you have to understand about my teaching and my style, I am very, very strict with my students about always including angles on their trig functions. Okay? If you don't have an angle on that trig function, it really loses its meaning. So our rule in my class is, if you're reading sine x out loud, you can say sine without the x. We'll assume that the x is the angle, but you can't do it in written work. So every time we write a trig function, we've got to have that angle in there. So again, you'll hear my students say the derivative of secant is secant tangent. I'll accept that verbally. Written, it has to be the derivative of secant x equals secant x times tangent x. So I hope you can understand why remembering tangent is going to lead to students being able to remember secant. We're using the same factors, just kind of in a different order. Where does cosecant come in? Well, we left off with the derivative of secant x to secant x tangent x, and now we want to figure out the derivative of cosecant. And this is what I say to my students. One of my favorite sayings I started saying, 3 or 4 or 5 years ago is, in math, we're not afraid of the equation. The equation needs to be afraid of us. And what I mean by that is we have all the power. If we want to change an equation, as long as we keep the balance, as long as we do the same thing to both sides, we can do pretty much anything we want to an equation. And I've said that over and over again. Remember, I've had my students in law and pre-calcs. They've heard this all throughout the previous year. So they know when I say we're not afraid of the equation, they're going to respond to me in unison. The equation is afraid of us. So keeping that in mind, I can do anything I want to this equation as long as I do the same thing to both sides. Well, it's kind of a little play on words on this one, as you're about to see, but the derivative I'm trying to take right now is cosecant. So how do I get cosecant out of this? Well, I'm going to do the same thing to both sides. I'm going to write co in front of everything on both sides. And when I do that, I get cosecant, the derivative of cosecant equals cosecant times cotangent. And it's got that same exact pattern as secant, except for it's all the co-functions. But my good students will stop me right there and say, that can't be right. And the reason is when we go back, when you look at that derivative of cosecant, you know the derivative has to be negative. So when we come back and we do this one, we fill it in with the derivative of cosecant is what we have on the other page, cosecant cotangent x. but the negative is already there for us. So now we can see patterns developing, okay? Where we had secant and tangent in the derivative secant, we've got cosecant and cotangent for the derivative cosecant, but because it begins with C, we've got the negative there. At that point in time, I go back here and I ask my students, who can tell me the derivative of cotangent? Can you follow this silly game that I've been playing, and can you use it to find a way to find the derivative of cotangent? And every year I get students who can come up with it because they realize, okay, let's reset the word bank, but this time the word bank looks just slightly different because we've got to have co's in front of everything. So when they reset that word bank, whoa, not that way. When they reset that word bank and they're finding the derivative of cotangent, what has to happen is we've got to put cosecant here and cosecant here. And again, when they go back to the other page, they're going to be forced to remember it's negative. So the derivative of cotangent is negative cosecant times cosecant, which I'm going to write as negative cosecant squared. These 6 derivatives, along with the derivative of x to the n, are the derivatives that I teach my students the very first day when we're doing our kind of our quick ways, our one-step derivatives. And I tell them, look, when you leave today, you need to know these 6. And with about 10 minutes left in the class, I have everyone close their book, close their notebooks, put everything away, and I go rapid fire around the room, and I just point to one of my students and I yell tangent, and they've got to say secant squared. Or I say cosecant, they've got to tell me negative cosecant cotangent. And this is just 5, 10, 15 minutes after we've learned the rules. If a student doesn't know it, because let's face it, they're not going to, some students are going to get put on the spot like that, they're going to be nervous, or they just might not be able to get it so quickly. Don't give up on your students. Ask them, what's the ratio you're supposed to remember? How many tangents to how many secants? And they'll usually remember that. And if they can remember that, that usually leads to them getting the final answer. So I'll go rapid fire around the classroom, asking them these derivatives, making sure everyone can answer at least one. And then for the next week or two, I follow them around the halls, and every time I see them in the hallway, I just yell out a derivative at them. They've got to say, if I see them in the hallway, I say, what's your sign? They've got to tell me cosine. And if they don't answer it, I just follow them to their next class until they do. It's gotten to the point now where I see them, I live in the town where I teach, and I'll see them at the grocery store working, and I'll go through their register purposely so I can ask them derivative questions. So it becomes a little game that I play with my students, and they get used to it, and it's just a fun kind of way for me to get them to remember these derivatives. Now, if you go back to that original sheet, I actually showed 13. These are 7. Remember, the other 3 are the derivative of the exponential functions, e to the x, a to the x, and the logarithmic function ln of x, along with 3 of the 6 arctrig functions, arcsine, arctangent, secant. When I do derivatives, the first couple of days, this is it. We just focus on these 7 so that we can practice our rules and learn our rules. Because to me, once you know the rule, bringing in another function is really the easy part. So I just want them to be good with their rules. So what I want to do with you guys now is I want to go through some of the samples I give in the beginning and talk to you about some of the pitfalls students fall into that if we correct them early, they're going to benefit when they get to these other derivatives later on. And another thing I always like to say, and those of you who teach will appreciate this, I want my students to know these backwards and forwards. Now, anybody who's taught calculus really understands the double meaning of that saying. We need to know them backwards or forwards. Today we're going forward because we're taking derivatives. But eventually, November is going to come, December is going to come. We're going to get to anti-differentiation. We're going to get to our integrals, and you're going to have to know how to use them going both ways. So let's take a look at some of these examples. Okay, so and keep this in mind as well. At this point, in the year, I have done the limit definition of the derivative. My students have computed many, many, many functions using the limit definition of the derivative. We've talked about a couple other rules, and actually I should go over those first. Let me just back up one step. We also talked about a couple of general rules of differentiation. You're all familiar with the derivative of a constant. All right, the derivative of a constant. So when we take the derivative of a constant, the answer is 0. Is that a one-step? Does that fit into a one-step? Because again, one of the things I say to my students, and I haven't stressed it tonight, to be a one-step, you must look identical to a one-step. So if we go back to these 7, and they start looking for the derivative of a constant in these 7, I'll get a large portion of my class saying, this doesn't match. And I can't use a one-step if it's not exactly like a one-step. So we have some discussion, and eventually a student will say, well, isn't that constant just a version of x to the n? And I'm sorry, x to the 0? And if it's x to the 0, can't we use that as our one-step rule? And that's one way of doing it. The way I prefer, though, is to talk about what a derivative actually means. And again, we've had all these discussions because we've done the limit definition. All of my students know that in words, the definition of our derivative is the slope of a line tangent to a curve at a point. So then we start thinking graphically. If we're talking about the derivative of a constant, what does that slope have to equal? Well, that constant has a horizontal line slope, horizontal line graph, so the slope has to be 0. So whether you choose to think about this using x to the 0 or just using it graphically, the derivative of constant is 0. And that's kind of like a little add-on I throw on to make sure everyone's familiar with it. Another one that I throw on is this rule, which again, you're all probably familiar with. If I have the derivative of a constant times a function, and I'll switch back and forth between k and c because we see both those as constants throughout the year. How does that affect the answer? Well, what happens is that k gets pulled out in front, and then we're just worried about taking the derivative of the function by itself. So this becomes k times f prime of x. In my world, in my classroom, we refer to this as the free ride rule. And the way the free ride rule works is a constant factor gets a free ride to the answer. So if I'm taking the derivative of something that has a constant factor, don't worry about it. Throw it in the answer and give it a free ride. And then the derivative of the function left behind will join it. So we get the derivative of constant is 0. We've got the derivative of a constant factor times a function gets a free ride. And then the next derivative rule that needs to be discussed to make sure my students are ready to do their homework, we call it kind of the common sense rule, but it's the derivative of terms. What happens when you take the derivative of terms? And again, most of us here know we just do it using what seems to be the logical way of doing it. We break it up and we take the terms individually. So this will end up being f prime of x plus g prime of x. And of course, since it's terms, it doesn't matter if it's addition or subtraction. It can be plus or minus. So I like to say term by term on this one. All right. So my students are very familiar with these names. The free ride rule. This guy down here is called term by term. And over here, this guy is the derivative of a constant is 0. You arm your students with these 3 general rules, and then you tell them to be a one-step. You have to look exactly like a one-step, and you're ready to go. You're going to be able to take on the first homework assignment. So the first night, I give them 20 problems. And what I do is I try to disguise the one-steps as much as I can. It's the only assignment my students have all year where they're at a huge advantage. They know every problem on this worksheet is going to be a one-step. They haven't heard product yet. They haven't heard quotient. They haven't heard chain. And I told them they don't have to use the limit definition. So I am making them become familiar with all the different nuances in turning things into one-steps. So when they do this one, we ask, is it a one-step exactly? And the first day goes kind of slow, to be honest with you, because I've got to get them used to the rules. We've got to ingrain these rules in their head. So we ask them, is it a one-step? And they're going to tell me no because of the terms, because it doesn't look exactly like a one-step. So they say no. But then another student will say, well, wait a minute, can't we go term by term? And then I go, okay, now is it a one-step? And when they go term by term, everyone looks at x cubed and says, yeah, that is exactly a one-step, no question about it. That's x to the n. When they go to the next term, the 2 root x, or the negative 2 root x, they look at that one and they're like, all right, well, I don't see x to the n. And some of your students may struggle with this, some of them may not, but I have students every year who still struggle with the idea of roots being rational exponents. So the idea here is to get your students to recognize the rational exponent, that's x to the 1/2, and use a free ride rule, because negative 2 is a constant factor. And the other pitfall that my students have that first day, again, they look at this one and they see division and they're like, there's no division in our one-step, so how can this be a one-step? But you know what? Where I'm going with this, the idea again is, how do we get x to the n from this? And negative exponents is something my students always need to practice early on. So I'm giving them all the practice I can this first night, because I'd rather stress it a lot the first day and never have to go over it again for the rest of the year. So I'm willing to take the extra time the first time we do it. So the last thing I want to tell you about taking derivatives that's going to be consistent throughout tonight's lesson and the next week, or I'm sorry, next time, which will probably be early next week when we're doing the implicit derivatives and the inverse derivatives. I ask my students, what do we take derivatives of? And the answer I give them is we take the derivatives of equations. Now, the reason I say that goes back to I'm not afraid of the equation's afraid of me. I can do anything I want to this equation as long as I do it to both sides. Back when I was a student, I would do this problem, and I'm going to model it for you. I would just be like, okay, x cubed, that's x to the n, 3x squared. Okay, no problem. That's a one step, I can do it. I'd go to the next one, and I'd be like, all right, how are we going to deal with this? Well, root x is really x to the 1/2. Again, something we've got to stress for our students. But once we know this, -2 is a constant factor. It gets a free ride. And now I'm just taking the derivative of this guy. So using the one-step rule, because it looks exactly like it, it's 1/2 x to the -1/2. So that is going to get written back in here. And then we go to the last term, because we're going term by term. And again, the idea is, can your students recognize how to write this as a one-step? Well, they know it's going to be a one-step, and let's face it, it's not going to be one of the 6 trig ones. So how do we turn this into x to the n? And again, this is my way of reminding them, let's use those negative exponents. Let's make that x to the -1. So in this one, positive 12 gets a free ride, and I'm going to take the derivative of x to the -1, which is -1x to the -2. So I'm going to write that right here, and I've got my right side done, okay? Now, when I was a student, I would just automatically put f prime of x here. I wouldn't give it any thought. If you'd asked me, why do I write f prime there? I would have said, because I'm supposed to. I mean, that's the name of this answer. It's the derivative. It's f prime of x. But one of the things that I'm subtly hinting at as my students throughout this is we take derivatives of both sides of this equation. The reason we write f prime here is because it is what I call the notational one-step derivative of f of x. So we're consistent. We're taking the derivative of both sides of this equation. Doesn't appear to be a big deal in the examples we see tonight. If you're back with me on the night we do inverses and implicits, it is huge. So I'm setting them up for what I know is coming later on down the road. One of the questions I'm sure I'm going to get is, how much simplification do we want? Okay. Well, that's really up to you as the teacher. And the reason I say that, in the AP exam on the free response section, no simplification is required. This would be a correct final answer if the question were to find the derivative. You don't need to do any algebraic simplification at all. Of course, on the multiple choice, you've got to match your answer to one of the 4 answers that are there. You're going to want to simplify this. I always think it's early in the year. It's a really good opportunity to start talking to our students about how we simplify these things. So the final answer I would expect on this one would be, let's see, that's going to be -1 over the square root of x, and that's going to be -12 over x squared. I want them practicing the simplifications, so I'm going to have them do this. So the reason for this problem is getting students to match it to the one-steps directly. We want them to make sure they look exactly like the one-steps they're working with. I just noticed that there's another question down here. I'm going to take a look at it. I'm wrapping up Unit 1, and I would like to test. I've been using the AP College Board to make quizzes, homework, etc., so the students can see how AP questions are asked. My question is, how would you format the Unit 1 exam? Okay, so to me, the Unit 1 exam to me is about, if you're going through your Unit 1, I need a little more feedback. Where does your Unit 1 end? To me, I want to make sure it mirrors some of the stuff they see on the College Board, but I also want to give them some deep thought questions. One of the questions I'm going to do in Unit 1 this week, and I hope none of my students are listening or I'm thinking about doing, is, 0 over 0 when you take a limit. What does that mean graphically? Because they see 0 over 0 in the algebra, and then they're just automatically going and they're saying, okay, I'm going to do more work and I'm going to do some algebra and I'm going to get this answer. But what does that mean in the graph? For the limit to exist, for you to be able to come from the left and the right, but not be able to plug in, what does that mean? I'm sorry, I should say get undefined when you plug in. And what I'm looking for my students to say is, the majority of the time there's a hole there. So, John, you asked me this question. If you could kind of give me some more info on where your Unit 1 ends, I'll be happy to answer you tonight, or even after the session is over, I can message you privately. The next example I'm going to do, and again, this is from that first night, trying to get them looking at one-steps, okay? They know it's a one-step, but it doesn't look exactly like any of these. So which one is it? And a lot of students the first day, they want to tell me the answer to this, and this is incorrect. They want to tell me the answer is 8 over cosine, because they see sine on the bottom by itself, and they're like, derivative sine is cosine. This is trying to get my students to understand the structure and how structure plays such a critical role in picking your derivative rules. So for this one, the idea is which of the 7 one-steps can we make it in? And again, we're just practicing our trigonometry. A sine on the bottom is the same as a cosecant on the top. If our students can recognize that, then they're going to know that f prime of x is the derivative f of x. 8's going to get our free ride. And the derivative cosecant is negative cosecant x cotangent x. Okay. We're going to go through a couple of these kind of quick because I'm just going to point out the pitfalls so that you'll know why we're doing these problems. This example, a lot of times I put it up and I'm in workshops and teachers are like, okay, this is a quotient rule. I'm just going to go and I'm going to do the quotient rule on this one. And of course, you can do it. It matches the format of the quotient rule. But I need my students to think a little deeper than that, because even though the quotient rule will get you a correct answer, okay, if a student sets up a quotient rule on this problem for me, I'll give them credit if they do it right. But then I'll write BW next to it, and that stands for better way. There's a better way to answer this, and I'm going to explain what I mean by that. The night we're doing this problem, it's a one-step. So which one of the one-steps is it, and how do I turn it into a one-step is the key. And the way you turn this one into a one-step is you make use of something called common denominators. It's really as simple as that. This is 3 separate fractions that have been added together with a common denominator of x. In my class, we call this splitting the fraction. And you can split fractions. The key is terms in the numerator makes us think split the fraction. So once I understand how a common denominator works, I can go backwards. Students are very, very willing to take separate fractions and add them together to get one denominator. They don't necessarily think of taking one denominator and splitting it up among the terms. So if we go through this, x to the 7th is on top of the first one, 2x cubed is on top of the second one, 5 is on top of the third one, and I've done no calculus. This is just rewriting the function. And as we look at this, it's still not a one-step yet. So now I need to make this x to the 6th minus 2x squared plus 5x to the negative 1. And again, now we can match all these as one-steps. You might be wondering, why bother? What's wrong with the quotient rule? Why not just take the quotient rule? Why stress to split the fraction so much? And if anybody has an idea about why I would do that, put it out in the chat. Let's see what you're thinking. There is a reason. There's a very, very specific reason why I stress this. And you're right. The quotient rule gets you the same result, but in a different form. But the College Board is going to accept that. So why stress this? The reason for it is because eventually we're going to integrate. And in derivatives, we've got products and quotients. In integration, we do not. Taking the derivative of this function is very nice. I've got a quotient rule I can use. But you try to integrate that function, and you're going to be really stuck if you don't know about split the fraction. So look into the future, think about the skills your students are going to need down the road, and start setting them up. I'll leave that derivative for you guys, all one steps there. This next one, again, the very first night, how is this a one-step? It doesn't look like one. What am I doing? I'm trying to get my students to remember their pre-calculus. I hope that they're going to see this as a trig identity. And once they see this as a trig identity, my students are not great at remembering all their trig identities, but they do remember sine squared plus cosine squared equals 1. So if I can get them to remember this, I'm not afraid of the function's afraid of me. I can divide everything by cosine squared. And my students can create tangent squared plus 1 equals secant squared. Very few of them have that one memorized, but they can create it. So now that I'm here, I know that tangent squared, bring the secant squared over. Tangent squared minus secant squared, bring the 1 to the other side, equals negative 1. And all of a sudden, this function is just equal to negative 5. So the derivative of a constant is going to be 0. So again, the idea behind this first night homework is getting them to recognize their 7 one-steps, but also getting them to understand that there's a lot we learned in pre-calculus and it's not going away. This is one of my favorite examples from early on. All of my students look at this and want to take the derivative of cotangent as a one-step, but what don't they realize? They lose sight of the fact that there is no variable in this problem. Cotangent of pi minus 1 is a constant, and notation comes to the rescue for us on this one. The variable in this problem is x. I look over on this other side, and I'm looking for an x, and there is no x. Without an x, it's a constant. The derivative of this is just very, very quickly equal to 0. And again, I'm setting students up for paying attention to who the variable is. That is going to pay off when we talk about implicit derivatives. It's going to pay off when we talk about integration. It's something they need to be made aware of. So that's why I like this problem so much. This next one, again, just looking at this and thinking about trigonometric definitions. Rewriting cosecant as 1 over sine x, we're going to see that this guy turns into a constant as well, and it's just equal to 6. The derivative here is going to be 0. So again, use as many examples as you can to get them to review their weaknesses in pre-calculus and algebra. So now we've done that assignment. They come in the next day, and I throw this problem at them. And I'm like, let's do this one. And they're like, well, can I take the derivative of each factor individually? And we all know the answer is no. So now they're like, well, then this can't be a one-step. And that's what I want them to say. If they're brave enough to look at me and say, this is not a one-step, they've got a good understanding. Knowing what you don't know is as important as knowing what you do know a lot of times in calculus. So when they say, we don't know this one, we have to learn something new, that's where the product rule comes in. So once they tell me it's the product rule, I go and I set up my boxes. And in this one, x cubed will go in the first box, cosecant x goes in the second box. And the beauty again is I just have to worry about one at a time. So when I'm looking on this side right here, and I say, is that a one-step? Does it look exactly like one? The answer is yes, so we can say 3x squared. When I'm looking on the other side over here, and I ask, is this a one-step? The answer, again, is yes. So we can write that negative cosecant x cotangent x. Stressing that we have to start in this bottom corner, I do my CRIS, and I get 3x squared cosecant x, and then I do my plus, and then I do my cross. So it's going to be plus, and if I look into the future, I'm going to see plus a negative, so I'm going to want some parentheses here. Minus x cubed cosecant x cotangent x, and then we take the derivative of the other side, and we get f prime of x. I can simplify this and do the plus to minus and make it 3x squared cosecant x minus x cubed cosecant x cotangent x, and that's where I would leave this one. But again, the goal here for me is to get them used to the structure of how to set up the derivative. You might be asking, why start on this bottom corner every time? Isn't it commutative? Don't we add the thing, the results together? And you're right. It doesn't matter on the product rule, but it's going to matter eventually. And you'll see that in the next example or two. And then the last thing I want to stress, every example early on, I ask, is this function times this function the original problem? If it is, your product rule is set up correctly. So we go down to this next example, and we look at this one, and we ask, is it a one-step? My students say no. We then say, is it a product? And the answer is yeah. So they've got to set up the boxes on this. Now, when they set the boxes on this one, the three factors usually throw them a little bit. But remember what we've been stressing. This first box times the second box has to be the original problem. So you got some choices here. I'm going to put 4x cubed in my first box. I could have done 4x cubed sine x. I could have done 4x cubed cosine x. I even could have done sine x cosine x. But I had to choose some combination of factors. I'm going 4x cubed in the first box. If I do that, that means sine x cosine x has to go in the second box. Well, here's the beauty of the boxes. Okay, think about how this is set up compared to trying to do this in your head with derivative the first times the second plus derivative the second times the first. I'm now just focusing on the derivative 4x cubed. I'm asking, is that a one-step? And the answer is yes with a free ride. So 4 gets the free ride, and 3x squared is the derivative of x cubed. Over here, I ask, is this a one-step? But the other thing you have to keep in mind is every time you ask, is it a one-step? It is a brand new problem. So all bets are off. Pretend the rest of the boxes aren't even there. Pretend we're starting with sine x, cosine x as the first thing you see. Is it a one-step? And the answer is no. But is it a product? And the answer is yes. So now for the first time, we've got to do nested boxes because we've got to take the derivative of sine x times cosine x. Well, now we're looking in this much smaller box, and we're asking, is the derivative of sine x a one-step? And that answer is yes. Is the derivative of cosine x a one-step? And the answer is yes. So now we've got to get the answer for the bottom box, the bottom right-hand box, and we're going to do that by, again, always starting down in this corner, and we're going to go CRIS plus cross for this guy. Well, by doing that, all that's really going to do is give us the answer to this bottom box. So it's going to be sorry, hold on a second. It's going to be cosine times cosine, which is cosine squared x. And it's supposed to be plus, but if I look ahead, I see this minus coming. So I'm going to do plus a negative, which is minus the sine squared x. And this is the answer to the bottom right-hand box. To get the final answer, we got to take it all the way out and start here and do our criss plus this cross. And we're going to get, simplifying this, 12x squared times the sine x cosine x box. And now plus, and we'll go the other way, and we're going to get 4x cubed. And this is where students are going to get careless. They're going to write cosine squared x minus sine squared x, and they're going to think they're okay. You've got to remind them, anytime you have terms in one of the boxes, the terms must have parentheses. You've got to use the parentheses there. So this final answer is going to be written the way I've got it. I am not testing them for simplification skills in this. I am testing them for derivative abilities. I'm accepting this answer. It's okay with me. I'm going to take the derivative of this side of the equation now, and I'll take the opportunity to remind them that we can use the Leibniz notation of dy over dx or y prime, and this is the answer we're looking for. To me, this is where the boxes are worth their weight in gold, because making big problems into small problems extremely beneficial for my students. The next example we're going to look at is a quotient rule. So they know that there's a rule for products. Now can they find the rule for quotients? They figure out there's got to be one. So again, going and setting it up with our boxes from the beginning, the numerator goes in this box every time. The denominator goes in this box every time. This is now a brand new problem up here with the 5. That's a one-step. The derivative of 5 is 0. It's a constant. X cubed plus 2, we go term by term. 3x squared plus 0. And now this is the part you got to stress with your students if you do this method. You've got to make them write equals and then always do the original denominator squared as the very first step. Stress it because they'll tend to forget it if you don't. And now you're going to understand why I'm making a big deal about starting down in this corner. Because in this one, it's not criss plus cross, it's criss minus cross. Since there's only one way to do it in the quotient rule, to me, let's just do it that way every single time. Be consistent. So I'm going to get 0 times x cubed plus 2, and it's going to be minus 5 times 3x squared. Again, as far as derivatives go, this is the answer. This one, let's face it, I'd probably have to simplify a little bit. We get some easy simplifications there. I'd probably have them do the 0, x cubed plus 2 minus 15x squared, and then over x cubed plus 2 quantity squared. I'd probably be happy with that answer. Again, I'm just looking for the derivative process, but I wouldn't be happy until they took the derivative of the other side and did that notational one where we say this is equal to h prime of x. So I hope through these examples you're starting to see how the quotient rule comes up. Okay. Oh, thank you. Times that 0, so I'd actually get rid of that. Thank you for that catch. So it would just be the negative 15x squared up on the top. Moving to the next one, okay? This is the one I save for the very end of class. I look at it, I wait till there's about a minute or 2 minutes left in class. We've been doing the quotient rule the entire time, and I'm like, go, take this derivative. You only got a minute, do it as fast as you can. And they just look at it, and the very first instinct they have is quotient rule. So they go sine x here, cosine x here, and the derivative sine, one step is cosine. The derivative cosine is a one step, negative sine. They're rushing, they're trying to get as fast as they can. Divide by that original denominator squared, cosine x squared. They're trying to get it in before the bell rings. And we've got the criss minus the cross. As we look ahead, we see minus the negative. So that's going to be plus sine squared x. And they get this answer, and they tell me this is my answer. Y prime equals this expression. I can't argue. Mathematically, it's right. But I always make sure there's just enough time to simplify it, because everyone will recognize my sine squared plus cosine squared on the top. And then I say, wait a minute, cosine squared on the bottom. Cosine on the bottom. I feel like we know cosine on the bottom. And then someone volunteers that, hey, isn't that just secant squared? And I'm like, yeah. And then I pretend, I play dumb, and I'm like, that sounds really familiar. Have we seen this derivative someplace else? And then someone will say, isn't that the derivative of tangent? And you ask, it is, but why am I getting it in this problem? And then the looks on your students' faces as the bell rings when they realize they did not take the question seriously when they asked, is this a one-step? That's a serious question. Can you make it a one-step? Because you could have saved yourself a lot of time by just saying this was tangent from the beginning. The last couple of problems we're going to look at is the chain rule. And I talked to you earlier today about using somethings. Okay, so when we do a chain rule, I have my students think about the 3 steps: the derivative of the outside, copy the inside, the derivative of the inside, and I actually have them write down who the outside and the inside is separately the first day. They struggle with the outside. They get the inside quick, though. So they'll look at this one and say, x cubed minus 6x plus 2 is our inside. And now for the outside, it gets tough because they want to do this. But we remind them that this symbol is not useful for one-step derivatives. And then someone finally tells me, hey, isn't it something to the 1/2? And because they're comfortable with using somethings, this is very, very seamless. They're like, everyone's comfortable. It's something like no one has a problem. So when we go to take the derivative of this example, the derivative of the left-hand side is f prime of x. Now we follow our steps. The derivative of the outside, well, that's the derivative of something to the 1/2. My students don't even hesitate to say that's 1/2 something to the negative 1/2. They're extremely comfortable with that. Step 2, copy the inside. That just means rewriting x cubed minus 6x plus 2. And then step 3, multiply by the derivative inside means setting up a parenthesis, and now asking yourself, is it a one-step? Start the process over. Term by term, these are one steps. My students will go and say 3x squared minus 6. And this is the answer to the chain rule. Do I want them to simplify? Do I want them to use their negative exponents maybe to rewrite this? Well, yeah, obviously, that's very useful for them to get used to their negative exponents. So I'm happy when they do that. I have the rule in my classroom, no negative exponents in final answers unless you start the problem with a negative exponent. So I would want them to say, okay, we got a negative exponent, which means we're going to have a fraction. This guy's going to have a denominator of x cubed minus 6x plus 2 in the square root. I'm going to have a 1/2. That 2 is going to go to the bottom. And then this factor is going to end up on the top. And I'm perfectly happy with leaving it at that. These next 3 examples are where students are going to struggle with the chain rule to begin with. They can do it when they can see parentheses. In these examples, the parentheses are understood. Get your students used to writing sine of 3x and putting the angle in parentheses. Because now the outside function is clear to everybody. It's the sine of something, and the inside function is 3x. So for this one, the derivative of the outside is the derivative of sine something, which is cosine something. Copy the inside 3x, and the derivative of that inside is the derivative of 3x. And that's a brand new problem. That's going to be 3. So f prime of x would equal 3 cosine 3x when we simplify this one. I'm going to skip over this one and go straight to this one because this is the one my students have the most trouble with. Where are the parentheses? Can you write this with parentheses? And if you can, life is good because this is going to be the secant of its angle 5x to the 4th, but that's all going to be raised to the 3rd because of the way the secant exponent works in this problem. So now we've got multiple nested rules. So we have to ask, what's the outside function? And to be an outside function, you've got to satisfy 3 criteria in my world. The outside function is always a one-step. It has to be one of those, for me at this point, 7, which is going to grow to 13 problems that they know. And because my students are comfortable with the idea of something being a variable, they're comfortable with this being a variable raised to the n. This is x to the n. It doesn't have to be x. This is x to the n, just so we're using something as the variable. So outside functions always have to be a one-step. Outside functions never have an explicit variable. And outside functions always use what I call a something. These two are saying the same thing. The reason we don't have an explicit variable is because the something plays the role of the variable. So some people might say, well, why isn't secant of something cubed the outside? Because I've got the one step, I've got the somethings, I don't have a variable. It goes back to this part. It has to be a one step. There's no one step that says secant something to the n. That's not a one step. That's why it has to be the outside function of something cubed. The inside function on this one, 5x to the fourth. So when we go through this problem, I'm sorry, I'm getting ahead of myself. The inside function on this one is not 5x to the fourth. It's secant of 5x to the fourth. So when we go take the derivative of the outside, it's this function we're starting with. It's 3 something squared. Now we go to copy the inside. And when we copy the inside, it's secant of 5x to the fourth. And now we've got to multiply this answer by the derivative of the inside. But the derivative of the inside is a brand new problem. So now I come down here and I'm looking at this guy and I'm pretending this is a brand new problem. So I ask, one-step product, quotient, or chain? Well, this guy is a chain rule. The new outside function is secant of something. The new inside function is 5x to the fourth. So we follow those 3 steps, but we have to write that answer in this parentheses. So the derivative of secant something is secant something tangent something. Step 2 to this one says to copy the inside, but this time the inside is 5x to the fourth. And now the new part of this is to take the derivative of this inside. Well, the derivative of this inside is this function 5x to the fourth. Whatever that derivative is, I got to put in these parentheses right here. So we ask, is it a one-step? And this time it is with a free ride. So we're going to get a 20x to the third on this guy. And then I always tell my students, be mindful of your parentheses, make sure they all match. And I think I need another parenthesis right there. Nested chain rules. Keep deciding who the outside functions and the inside is by breaking it down layer by layer. I want to do a couple more examples this evening, but I'm a little short on time. So I want to leave you with this one right here. This would not be on my first night of homework. I don't do the exponential base E the first night and come back, but my students struggle with it greatly. And it's because of where the outside function is on this one. This outside function, if you're going to write it out, you've got to use e to the something. And students are not comfortable with that. But if you remind them that the one step that this looks the most like is e to the x, the outside has to be e to something. And then the inside on this one is going to be cosecant of x. So if we take the derivative of the outside, the derivative of e to something, well, the derivative of e to something is e to something. Copy the inside, cosecant x. And now the next mistake my students want to make is they want to put the multiplication in the exponent. Tell them these 2 steps are separate. The third step is to be a new factor every time. So when we do this, we're taking the derivative of cosecant. The derivative of cosecant is a one step. That's negative cosecant x, cotangent x. The derivative of the other side here is h of x, h prime of x. So there's our final answer. Tonight, what my goal was to develop kind of a process for taking derivatives. The main components of this system, to be a one-step, you have to look exactly like a one-step. Okay? Terms take their derivative term by term. You can split them up. A constant factor gets a free ride. A constant by itself, the derivative is 0. Those are the main rules for the one-steps. Then, to set up your product, to me, the boxes make big problems into small problems, and then it's criss plus cross. The quotient, same thing. Big problems into small problems, criss minus cross, don't forget the denominator squared. And then the chain rule, 3 steps, derivative of the outside, copy the inside, the derivative of the inside, keeping in mind that you can only be an outside function if you satisfy your one step, you don't have an explicit variable, and you do have a something. So I hope you guys can take the information tonight, incorporate this how you see fit in your own classes. I'm going to be coming back most likely Monday of next week, maybe Tuesday. I'll send out an email. You can check it on Fiverr, talking about broadening this to handle those inverse trig functions, inverse functions in general, and implicit derivatives. And you're going to see that a lot of the work I did today doesn't seem important for these problems, but becomes extremely important when we do that session 2. So I'm going to stick around for a few minutes and answer questions, but thank you for joining me tonight. I appreciate your time, and I hope to see you again on Fiverr. So for the questions, John, if you're still out there, I'm talking to you. John ended his unit 1 with the intermediate value theorem. Unit 2 is derivatives. So over an interval, taking limits of function with direct substitution. Okay, so your unit 1 is strictly limits. Okay, so there are a lot of great problems on the AP stuff that you can take and definitely incorporate them, get them used to taking limits and the AP style problems as much as you can. Do graphical limits. There are some new graphical limits that are being released that are really, really far more complicated than some of our older ones. Matter of fact, I did a stream that you can check on Fiveable on graphical limits. I introduced a bunch of them in that stream. So if you need help with that, John, you can message me directly. You know how to reach me. But I would really just focus on them knowing how to take those limits and doing those indeterminate forms. That's the big thing. And it's kind of funny. On the AP exam, they're going to have L'Hopital's rule on their side. They don't have L'Hopital's rule in my class when I give this exam. I am making sure that they can do the algebra because that's going to pay off in derivatives. That's going to pay off in integrals. So I am not giving them L'Hopital's rule for this exam. I'm doing it the old-fashioned way. What I can do for you, John, is I can send you a copy of one of my older exams. You can take a look at it if you want, and we can kind of message that way if that's all right. For anybody else that's still sticking around, any questions that you want to ask while we're here? All right. Well, then, thank you for joining me tonight. I look forward. I'll be doing a stream on teacher development once a week for the next probably 2 months. I'll be doing it. So I'm looking for more topics. The next topic, again, early next week, is going to be more derivatives of implicit derivatives and inverse functions. Then for you BC calculus teachers out there, I've got a lot of requests for polar calculus using polar graphs. And BC, not too far down the road, we're going to start introducing the idea of Taylor series and sequences in series. But if you've got something else you want, shoot me a message on the chat in the next 30 seconds or email me directly or tweet at me at my Twitter account, and I'll be sure to include that in future streams. So thank you for joining us tonight. Hope everybody has a great night and that your year is going well. If you enjoyed it tonight, just let me know in the comments, or if you have any feedback that you'd like me to have, please let me know, and I'll be sure to incorporate it in our future streams.